in the S matrix that you want. And in that file, it lists all the frequency, like within that frequency range, what's your S parameters, S11, S21, and S22, and so on. And then usually it's not matched to 50 ohms over a wide range of frequency. And you need to decide, okay, I'm going to use this in this frequency range. And so you design a circuit to match that impedance from the S parameters that you have to 50 ohms. So the amplifier will see a good match at that frequency, right? So that basically what you do, you match the impedance, right? I mean, very, very oversimplified statement, but that's, in a nutshell, that's what it is. So let's look at, oh, I have not shared this with you yet, huh? Sorry, I thought we were looking at this. Are we? We're good, right?
Yeah, the impedance matching Smith chart slides.
Lecture notes, yeah.
So, so why match? Why do we want to match impedance? Well, we talked about this already, right? We want to minimize reflections, because if the impedance does not match, you always have this gamma, this reflections. That means some of the energy is going to be reflected. You're not maximizing your energy you want to send to the devices, right? And high frequency power is expensive. Low frequency, if you do a bipolar transistor or op amp, those are cheap. But at high frequency, if you do a power amp, that could be like hundreds of dollars, hundreds of thousands of dollars, 100K. You can do a company just it's a huge company just doing amplifier by itself. Of course, there are many type of amplifier, so so paying so much money for the power, you don't want to waste any. You want to maximize your transmission power, right? So that's why you want to match. So and also when everything match, when we look at the transmission line theory, if the low match with the impedance of the transmission line, let's say all 50 ohms, then the line length becomes not important. It's not like, oh, I have to be very careful laying out my circuit. I cannot have more than 1 mil longer or 10 mil shorter. That would be disaster if the impedance not match. So when you match the impedance, then your 50 ohm line length becomes not important, right? Because you can see that from the formula. And we also look at the power point of view. If the impedance match with the generator, which is 50 ohms, then you deliver the maximum power to the load, right? Which is 1/2 of the power available from the signal generator. So that's the goal. So in other words, we want to be able to look at any load, anything you connect, either is a transceiver or a mixer or whatever devices. You want to be able to design a network, right? A matching network. So when you look into here, it's always 50 ohms. That's the goal of this chapter. Okay. So how do I do that? Okay. So, and we also talked about this circuit before when we were doing transmission line. We are looking at the stub, right? We say there are transmission lines sticking out for no reason. Those are called stub, open stub. And then I also say RF circuits is for the longest time people call this like a black magic. It's a black box. Because let's say you design, this is a low pass filter, you design it, laying out, put the circuit together, and you connect everything from an input to output, and the circuit would not work, or will not work as well. And then you give it to the technicians, and they just using a Q-tip or toothpick with some gold ribbon or copper strip or dielectric block. They poke around, and then they'll make it work, right? So they are the magicians. Exactly what are they doing? I mean, why would they poke around and make things work? How can you? Why is it not working to start with? Well, the circuit is not working because so this is a 50 ohm line. This is a transmission line, 50 ohms. Going into here, coming out here is also 50 ohms, and 50 ohms go out. But the problem is, you see how this circuit is laid out in 3 pieces, right? Every time you have a junctions, when the signal coming from here and here, at this junction, there's a discontinuity. That gap here is not 50 ohm line. That's not 50 ohms. So now you're going from 50 ohms to something we don't even know what impedance it is. A lot of the signal would be flat back. And we go to here, it's the same thing. So every time you have a junction, you have a mismatch. The impedance is not 50 ohms anymore. So when they poke around, so you see all this chicken dot around the transmission line. Sometimes people do that because when the technicians tune it, I don't know if you can see. Can you see? Let's see if I can zoom it out. Can you see the little gold ribbon line out here? Yes or no?
Faintly, yeah.
Okay. So let's see if I can point this out. I'm gonna take this out. This piece here. Is that, you see that piece of ribbon? Right. So when the technicians, I'm going to take this out also. And this piece here. Around the corner. Do you see that? See a little bit of, okay. That's what they do. That's how they make it work. That's how they tune it and make it back to 50 ohms or close to 50 ohms, right? By putting a piece of ribbon somewhere along the transmission line. This one is very obvious because this is the band. When the transmission line bend, this portion, the impedance also changed a little bit. So putting a ribbon here makes sense. Putting ribbon here, you have to, that's close to where the junction is. That makes sense. We'll talk about what does that mean. I mean, mathematically or in a transmission line model, exactly what does that mean? Okay. So this ribbon here is to match the impedance. Okay, it's one of the techniques that we're going to talk about for impedance matching.
I have a quick question that's just related to that photo.
Yes. Yeah, what about it?
Is there any way to tell, just by looking, if a stub is open or shorted? Because if it's shorted, wouldn't there be like some kind of VF connected to the
right?
ground
Okay,
line?
so yes. So when you look at this diagram here, this is called single stub. I'm trying to see where the view is. Sorry. I'm trying to zoom in out. Okay, so by looking at this, do we know, for example, this stub is that open and short, right? So what do you think this is? Is that open stub, short stub? Is that a shunt stub? Is that a series stub?
It looks like it's shunt.
Is that open or short?
It depends on whether those little squares are connected to ground or not.
So you have all those little tiny square, they are just printed down. It's like a printed chicken dot. We call confettis, right? On the circuit. So this is a microstrip. This is the bottom is ground. And on top you have the active trace. And on the side you have a tiny chicken dot. Something like that.
But how can the little tape, how can that create a stub? Isn't that just a connection? Doesn't that just keep the signal going?
What connection from where to where are you thinking?
So the area that you circled, is that, so that's just a vertical connection, right?
No. That's this connections here I'm drawing. Let's see.
Is there like a sideways piece of tape on there that I'm seeing?
Yes. So if you look at from the top view of what I'm drawing here, this is the substrate. This is the bottom is ground. On top here, this is the active trace, the 50 ohms. That is this trace here. And then on the side, you have like a little confetti printed on top of the circuit. The reason this confetti is there because after I load, I put a gold ribbon or copper ribbon on it. How do I make this stay, right? I mean, after I finally find the positions, how do I make this piece of copper tape stay at that positions? I have to get weld it. I'm gonna have to weld it to some kind of metal, and that's what I'm welding this to the active line and to the confetti. So this is the connections. So if you look at it, this is really a transmission line, and it's a shunt stub because this confetti and this ground becomes the shunt, and is that open stub? Oh, is that open stub or short stub?
Looks like open, right?
Open. So this is an open shunt stub. Okay. For microstrip, open stub is a lot easier to make than shunt stub. You can people can drill holes. You know, people can drill holes from top and to the bottom and fill it with metal. Those are called via holes, right? Or VIA. And though that process is commonly done, but usually it's a more expensive process, and people try to avoid if they can.
So is that what the impedance inverters are for?
He's so cute.
In designs?
To make it either parallel or like
What are you doing up
series
there?
or shunt.
Come there.
Is that right?
Well, if you were, you could convert a design that requires a short stub into one that requires like an open circuit, right?
Yeah. Why are we picking? Yeah. Okay. I'm sorry. Say that again.
I said, I mean, let's say that your filter requires like I'm sorry. If your filter requires a short stub, but you are using microstrip to realize the circuit, then you use the impedance transformer to get an open.
Yes.
Transform it
So
to
they're
an open.
equivalent. We're going to talk about how do we use stub for impedance matching later, right? You can always choose what stub you want to use.
How is that a shunt, not a series stub?
Because the connection is drawing is the top and bottom.
I thought you said it wasn't going through, so it's never touching the bottom.
Yeah, so open stub never touch the bottom, right?
Right, but when I'm looking at the picture of the shunt, it's looking at, it's going from both ends, both transmission lines. You know how we draw the two transmission lines?
Yes.
It's going, bridging both of them.
Bridging, what do you mean by bridging?
Um,
You never touch. So here I have my transmission line. I do a shunt connections here. open stuff, right? They don't touch. The ground is always on the ground. The top trace. So if I draw this as a microstrip, I have a line here, and then on the side I have a line. Open stuff, right? So this is my in, this is my out.
What would a series stub look like on
on microstrip? On microstrip, to do a series stub, you will have to, let's say, again, this is the side view of a substrate, and this is the ground, right? So the ground is here. So I have a series stub, an active line going to the top, active line going to the top, and I want to do a series open stub, for example, then I would have to solder a piece of metal here, solder a piece of metal here. So on the active, that means when I draw a line here, I will have a little gap, for example, looking from the top view, and I'm going to solder a little bit of piece of metal sticking out of the plane in 3 dimensions.
Okay, I see.
Yeah. So this is a little bit harder to construct, but it's done all the time. I mean, Sam would see a lot of this being done in the lab. Okay. So this, again, let's go back to this tuning here. So again, the conditions in this case would be just poke around with the ribbon and try to find the spot that make the circuit match. How does it know it match? Well, by looking at the S parameter. So, and the instrument we use to look at the S parameter is called a network analyzer. You look at this, your network, right? We're going to talk about that a little bit, hopefully later.
So for the technician, do they just randomly pick
Yes.
some? Okay.
They do not do calculations. They're not engineers. They do not understand why this works. They just know it works. And they know what spot it tends to work better. So they just keep, kind of try and error. But as an engineer, when you go in, you should be able to explain or understand why it works. So this kind of tuning, you can understand it by what we call the single stub tuning. So what does that mean? So here, I have a transmission line. I have an impedance that I need to match. I don't know what this impedance is, but I know I need to match it. So somewhere along the transmission line, by putting a open stub, you can think of it as a shunt capacitor, right? Because the ribbon to the bottom ground is a parallel capacitor, right? So you can model that to start with. You can also model it as a stub. We're going to talk about that later. So I'm going to assume this is a capacitor here. And then I'm going to slide that capacitor. How big the capacitor? Well, is determined by the size of the ribbon. The bigger the size, the bigger the capacitance. So, and I'm going to slide the capacitance along my transmission line. So my length is variable. I'm going to slide it until I could find a good match, right? That's what the technicians do, right? Okay, so let's assume my impedance is not 50 ohms, but somehow becomes 50 minus J10. Okay, and so in order for this to work, let's do some calculations. So the normalized impedance is just divide everything by 50. That's normalized impedance. And then the admittance is 1 over Z, right? So I just calculate what is 1 over Z of this, the reciprocal of that. And then I want to, looking in from this side of this transmission line, the admittance, we call it Y1, right? Y at this location, I'm going to call it Y1. What you want is you want Y1 to be equal to the characteristics impedance of the system minus some susceptance. In other words, by sliding it at the right location, you want the admittance to be matched of the real part already. You only have to cancel the imaginary part later with the capacitance. Is that clear? Okay, for the two elements or the two steps tuning, you always want the first element to cancel something. Usually it's the real part. And then you want the second element, in this case is your capacitor, to cancel the imaginary part. Okay, did I make myself clear? You slide these ribbons until the real part match the real part of this 50 ohms, which means what is Y naught here? If 50 ohms is what I want to match, what is Y naught?
1/50.
1/50. That means you want to slide, this is 1/50. Okay. You want to slide this until you see at least very close to, if not exactly, 1/50. And then the size of the ribbon, hopefully you pick the right one, would match it, right? Okay.
So what are we sliding, the load or the capacitor?
The ribbon. In the last picture is the ribbon.
Right.
The technician is sliding the ribbon. Right?
Can we see where the ribbon might be on this transmission line there? Is it possible to show that?
Here. So equivalently on this picture, I'm looking at this, right? The input, for example, my return loss S11 is poor, and
right.
I'm going to slide this ribbon, right? Okay.
Yeah.
So this is my low. I mean, and assuming this is not 50 ohms, so I'm going to slide this like at different locations. I'm just going to slide this ribbon up and down in certain locations. So
okay.
by choosing the location, I'm actually doing this, right?
Right.
Okay. So the step is, the first one, I'm going to match the real part, and then hopefully the ribbon can match the imaginary part. Does the technicians know how big the ribbon to use? No, he just keep trying. What if this capacitor doesn't match, doesn't cancel this imaginary part? No problem, but at least it get closer, so I can see the return loss from like -5 dB. Well, it improved to -10 dB. I already gained the 5 dB. Then I'm going to use another ribbon and do the same thing. Every time I put a new ribbon on, it gave me 2-3 dB. That's fine, right? So that's how the tuning process goes. You just want to get better and better and better.
I have a question.
Yes.
How does moving that along the transmission line change the impedance?
Oh, so now you forget what you learned in transmission line. Remember the impedance looking into the low. So let's say this is 50 minus J10. But by sliding this out, my impedance changed. My impedance, if there's a mismatch, my impedance is a function of the line length, right? Because it's periodic. I have a tangent beta L here, right? Remember we say I put 100 ohms here, looking into the transmission line, I do not see 100 ohms. I can see a capacitor, I can see an inductor, I can see an open circuit, I can see a short circuit. I can see anything I want to. Depends on how long this transmission line, what is the impedance of this transmission line, right? The impedance of an active of a RF circuit is not constant. You put a 50 ohms here, you don't see a 50 ohm unless the transmission line is also 50 ohm. Right? Remember that discussion, all those calculations in transmission line chapter. The Z in is not constant, depends on beta L, depends on L. Right? Okay. So that's exactly what we're doing. So the first step, so anyway, let me go back to here.
Wait, one more question. So,
yes.
Like if we were gonna do this as a transmission line problem, and let's say you move the capacitor halfway through the transmission line. That's
Yeah.
right at the half. So would you, when you drew that out as a transmission line problem, would you have then 2 chunks of transmission line and then the capacitor in between?
Yes.
Okay.
Yes, but if I continue to say, you say, well, but then that means you have an unknown length of a transmission line on this side, right? Before you connect to your source, right? But this is 50 ohms. If by doing that I see a 50 ohms already, then my problem becomes, yeah, I have a 50 ohm line transmission, 50 ohm transmission line here, and my source is here. But now this equivalent, this load, is no longer CL, is match input. That's 50 ohms already. So if they both are 50 ohms, remember, then the line length becomes insignificant. You can have any line length that you want, assuming there's no loss, right? So that's the idea.
That makes sense.
Yeah. I'm glad you guys are asking all these questions. You should have a lot of questions because, yeah, that means you guys are thinking, you know, in the right direction.
I have a
Yes.
question.
Yes.
Would it be physically meaningful, you know, to put the capacitor after the transmission line?
Which transmission line? You mean this transmission line?
No, the next one.
You mean this?
Yes,
So you mean putting the capacitance first?
just before the load.
You mean like right here?
Right.
Yeah. And
Can the same effect be achieved?
no. So by putting a capacitor here, let's say you assuming you can only match one. Remember, this is a complex load, right? The impedance, the real part is called the resistance. The imaginary part is called the reactance, right? So if you want to match a complex number, you have to match both the real part and the imaginary part. You cannot use one parameter to match both, right? It's like solving a simultaneous equations. Two variables, you need 2 equations, right? So now you have 2 variables to equalize or match. You need to have 2 elements, 2 variables to match it, right?
So you're using a capacitor because it's a purely imaginary impedance, and you already have a 50 ohm transmission line, so you need to add an imaginary impedance.
Yes. So and you can use L, you can use C, you can use series, you can use shunt, right? You have a lot of choices. You can use stub also, and which is what they do. But the reason we say C, because I can model the physical picture. Again, we have a substrate here, and the ground is at the bottom. The transmission line is here, the stub lay on top of it. So looking at the stub and here, that's an open stub, but you can also model this as a capacitance, right? Shunt capacitance. So I just, for simplifications, before we talk about stub, I'm just going to use the capacitor.
So is that why okay, so you're saying that the little strip that you placed on the board that you
Yes.
showed us,
Mm-hmm.
because it's wider, it has a larger capacitance?
Yes. Yes. So I probably have not talked about this very much. So if you look at the transmission line, okay, so some lines are thicker, some lines are thinner. So let's say the signal is going from here to here through a very thin line. A very thin line is very high impedance, right? So to lay out a board, you can go to AWR and play with the tools by putting a very narrow, the width of the line is narrow, your impedance go up. So the impedance purely depends on the width of your transmission line. So if you use a very wide piece of transmission line, that impedance is very low. So low impedance is, so like here. So going in here, going through this, that's very narrow line. So that's my high impedance line. Going through from here to here, that's very wide, right? This is the width. So this is Y width, so this is the low impedance. So high impedance is equivalent to inductor. Low impedance is equivalent to shunt C. So this is series inductor. This is shunt capacitor. So I have high, low impedance. This is one way to do a low pass filter. So this is a low pass filter network.
We had an example, or there was a picture in the slides. I think you said, or there were like looked like little coils or springs. So
Yes.
And then you said those were basically like inductor.
Yes.
They're like inductors. So is that because of the length?
No, because coil, right? Coil is that's how we do inductor. It's a round of coils of wire. So because
you can
by
use,
yeah, by doing that, remember the electromagnets, right? When you have a coil, there are currents going around the wire, then you store magnetic field around it.
you can use a literal coil as an actual, like as a
Yes.
physical inductor, not just a model.
Yes, but that only works for relatively low frequency. So again, people will do this typically to 1 gigahertz, 2 gigahertz max. So if you want to build circuits at like for cable TV 12 gigahertz, that is like very difficult to control. So at high frequency, so at so you need some kind of inductance, and so you have a coil around a winding of coils. So at higher frequency, because the impedance is J omega L, right? At higher frequency, that means you want to lower your inductance. So a very high frequency, your number of turns usually gets smaller and less. And when you go to like 1 Henry, you're basically just a wire, jumping from one side to the other side with a little jumping loop. That's already a lot of inductance. So, but exactly what is the inductance? That becomes very difficult to calculate. So even higher frequency, this wire, this loop, basically just a line, right? Nobody would do that. But a line is basically is a high impedance line like this, just a line going from one place to another, right? Or you can think of the high impedance line. The magnetic field is going around the current. The current is going on this strip. So the magnetic field going around, so it stores magnetic energy. So that's why high impedance line is equivalent to a series inductor.
And then we wouldn't see so much of those field lines with something that's got a wide, like the low
coil,
those big patches.
The big patches, you see more of the electric field because you have a big area between the two surfaces.
Yep.
Right? So we have not talked much about this because transmission line theory apply to all type of transmission line. Now we're only looking at one very specific type, the microstrip, right? So so before we go into too detail in one particular type of transmission line design, this is still in general. This is still right. This is still in generally true. So we are down to here. I know the low and the admittance after the transmission line I call Y1. I want to match the real part already, leaving the imaginary part being variables. I don't know yet. Right? So that means the normalized Y1 is equal to normalized to Y0. That's 1 minus B with a bar. Again, the bar on top means normalized. So this is a normalized susceptance.
Professor?
Yes.
So what does B represent again?
Susceptance.
Oh.
So Z is the impedance, right?
Yeah.
So Y is equal to 1 over the impedance. That's admittance.
Yeah.
The real part of impedance is resistance, and the imaginary part is reactance. The real part of admittance is called what?
Conductance plus
conductance, and the imaginary part is called the susceptance.
All right. Okay, that makes sense.
Yeah. Erase this part. Okay, so again, I want to write this admittance looking in here is 1 minus JB. So, and then I'm going to use this formula. Okay, and so my Y naught is what I normalize. So that's my Y naught here. Okay, plus J tangent beta L. Instead of writing tangent beta L every time, I'm just going to write T. So T is the same as tangent beta L. I just don't want to write it out all the time, right? And that's the bottom. And you do some algebra, you cross multiply. So you get this, the second equations after you cross multiply the first equations. Now, this is a complex equation. What does that mean? That means there are two equations in it. One equation is the real part is equal to the real part. The second equation is the imaginary part is equal to imaginary part. So to match the real part, so this is the real part of the left-hand side. This is the real part, right? So the real part on the left-hand side have two terms, these two. It's equal to the real part on the right-hand side, which is just this term. So I get this equation, the real equations, right? So now I can solve for B or B bar in terms of T. So I just do some algebra and solve for this. And then the imaginary part of the same equations. Sorry. The imaginary part of the same equations. This is imaginary. This is my imaginary part, right? Or these equations. That's equal to this. You see, it's equal to the imaginary part on the right-hand side, which is this. And that's just this. So again, the imaginary part is equal to the imaginary part. And I'm going to solve for B again as a function of T. So, so I get these equations. Now I have two equations, two unknown. You just do your algebra, solve for, eliminate one of them. So I eliminated the B, and then I get a quadratic equations like this. So by solving this complex equations, we get to one of the relations is this. And quadratic equation has two solutions, right? So one is T is equal to this, the other one T is equal to that. So let's look at the two solutions. So T is equal to the first one. Again, what is T? T is tangent beta L. That means I can solve for beta L. That means I can solve for L. So L is equal to 0.009 lambda. And once I know T, I can go back to any one of these equations and solve for the other variable, B bar. So I plug that back into here. I'm using these equations here. Right. Plug it in here. I solve for B. B is equal to 0.497. And so B, that's normalized, right? To unnormalize it, I have to multiply by Y naught. Y naught is 1/50. That means I divide this by 50. So I get B is equal to minus 0.01. So what does that mean? What is B? Well, this is the capacitance, right? What is the susceptance for capacitance? What is that? Or what is the impedance of the capacitance, let's just say?
1/JC or J omega C.
Right, so the impedance of a capacitor, of a shunt capacitor, is equal to 1/J omega C, right?
Right.
So this is equal to minus, right, so it's equal to minus JC.
Minus
So,
J.
but what is the admittance of a capacitance then?
Minus J omega C.
Minus?
No, that's just J omega C.
That's just the omega C. So that means this is my B, right? JB. My B is just omega times C, right?
Right.
That means the admittance of a shunt capacitor has to be a positive number. Are you with me? Because it's j omega c, omega is positive, z is positive, so this is always a positive number. But because this is negative, that suggests that this is the shunt. You cannot use a shunt capacitor. It has to be a shunt inductor. If you want to use it at this location, it has to be inductor, right? So, but since we are using a capacitor, this is not a valid solution. Are you with me? Okay,
So in this case, would you put it just a little stub, not like a capacitor, like not like a wide strip? Just
oh,
like
no,
a really
no,
narrow
no, no,
strip?
no, we're not done yet. So in this case, that means this is not the solutions. Remember, mathematically, we have two solutions. Does that mean both solutions are physical realizable with the circuits that we have? No, in this case, the first solution doesn't work. The second solution, however, when t is equal to 0.671, if you solve for beta L, and so you get L is equal to that at a different locations. But when you plug in to solve for B, now B is a positive number. And if B is equal to my omega C, I can solve for C. That means this is, if I know what frequency I'm matching, I can tell you what capacitance do you need at that location.
But I mean, couldn't you still use the top one and just use an inductor somehow?
Yes, yes, but that doesn't describe the process the technician is tuning.
I see. Okay.
Right? Yeah. So in this case, this is how a single step tuning works. Any questions?
So the technicians has option whether you want to use inductor or you want to use capacitor?
No, because again, we are looking at a microstrip circuit, right?
Right.
So I have a top trace here, I have the ground here. To do shunt has to be an open stub. I'm not physically connecting anything from the top to bottom. I'm just sliding a piece of metal on top.
Right.
And so if I want to do a shunt inductors, I have to physically attach this and drill a hole, make a very small hole. Right. So that's not the process. That's an expensive process. That's more like a V hole. So I have to drill with V holes. I cannot keep drilling the circuit board and make a V holes and try if it works or not, because that screw up my circuit also, right? If it doesn't work.
Right.
Right. So physically, I'm just trying to describe the whole process, right? So now you understand what the technicians are doing in the lab. Why would they, by poking at certain places, how come the whole thing all of a sudden would work? All of a sudden the signal would go through and return loss is good and the loss is low, right? And that's the reason.
So, Professor,
Yes.
for the L that we have here that you're solving for, is that the length of the transmission line, or is that the length of the where we want the capacitor to be at?
Yeah, the usually is the location of where you put your stub. So here, for example, looking at from the bottom, right? So let's say if I'm looking at the bottom, I put the stub here. So this is my L. How big is the ribbon? That dictates C. Right?
Where's your load in this picture?
I'm looking at here. So for example, the whole thing is what we call the load, including the 50 ohm on the other side. Okay. Here, so one thing I want to also point out is whatever the picture I'm doing right now, we're only looking at one port network, right? In reality, this is a two port network, but I'm assuming one port network.
Wait, I'm confused because if that bigger chunk is the load, and we're looking into it, isn't the L the length of the transmission line that we're looking into?
From the load. Okay, so let me define.
From the load?
Yeah. So we are looking at one port network. So that means, or assuming everything is good. So assuming this is 50 ohm and I put a load in here to ground, 50 ohm to ground, right? So looking into here, that becomes my input. So I'm saying, for example, all this piece of transmission, all this piece of substrate, including this piece, including my termination, whether this is the second port 2 on the network analyzer, that all considered as the load from looking at here. So I have a transmission line here, 50 ohm, and then to a load, including this junction. So let me, right?
So that's looking at it from one side, and
One side only.
So if the technician want to look at it from the other side, then he would consider the
right. That's yeah. So that, I mean, in reality, we need to do a 2-port network. But right now, let's say I have a circuit, right? I don't know what that circuit is. Just a circuit, 2-port circuit. On this side, I'm terminate this at 50 ohms, right? And here I have a piece of transmission line in front, 50 ohm line, and that's this piece of transmission line. And so I'm saying, looking in here, which is from the bottom end, I'm going to call that input, for example, right? Looking at here, I want the technician to slide a capacitor here, somewhere along the transmission line. And then, even though this whole thing together, I'm going to call it Z load, because I don't really care what that is. Just a Z load. By sliding the capacitor, the stub on the transmission line, now looking into here, I see a 50 ohms. But even though
where's the L in that picture? Is it on which side of that tiny circle is the L?
Tiny circle. What tiny circle?
Where you circled the 50 ohms there on the transmission line? So you put a capacitor somewhere on that transmission line. What side of that capacitor is the L?
What side? So here. So that means I'm going to call this whole thing, including the low and everything, I'm going to call this ZL, right? Including the junction.
Yeah, right. I'm with you there.
L would be the line from here to where I put the stub.
Right. Okay. You said the opposite last time. That was confusing.
Okay. Sorry.
Quick question on
yes.
On the next slide.
Okay.
So the negative 0.01 that we got for the first solution, so
yes.
Are we able to use that in any way? Or does that just tell us that we got to stop and then we have to solve for what an
so if you can calculate it, and that's the result, you could use it if you want. So you can, at that location, because we know what L is, right? We know what location. I can drill a hole. I can make a little tiny inductor and stick in there, right? We can do that. But more than likely, for the circuits that we have, no one is going to do it. We just say, okay, that's not the best solution. The second solution is a lot easier to do, a lot easier to achieve without drilling holes and all that. So in practice, no one would do the solutions on top, in other words.
Okay.
That also ties to exactly what physically, what circuits you have. For high frequency circuit, a lot of times people use the substrate called alumina. Alumina is like a white, is a hard board, hard material. It's not like a Duoy 5880, which is very flexible. Those circuits are more like crystal type, right? It's very hard. So more like glass. If you want to drill holes in it, it has to be very careful. I mean, you can easily crack the glass or the substrate, and that becomes useless. Right? So that's why drilling real holes on a hard substrate like alumina is a relatively expensive process. All right, so that's one type of tuning. So is that all we need to understand tuning? No, that's just the traditional way to do the tuning after everything is designed and supposed to be 50 ohms, right? And when you put it together, your 50 ohm circuits becomes not 50 ohms because of a lot of reasons. Anytime you have a junction, you break the 50 ohms. Depends on the surrounding. Remember, if the circuit is too close to the wall, the electric field, might connect to the wall instead of to the bottom ground. So you change the electric field or magnetic field patterns. That changed your inductance or capacitance, and so that will change your impedance, and so your impedance becomes unknown. So that's why a lot of times when you put the circuits together, if you don't consider every little details, it will not work, right? And you cannot even model it because it's hard. Let's say you are putting it next to the wall. How are you going to model the capacitor? It's very difficult. So so that's why tuning on the bench becomes very important, and that's what the technicians usually typically do. Okay. But if you have to design something, for example, we said earlier, if you want to design an amplifier, you buy a semiconductor chip and you have to design a matching circuit. You won't rely on the technicians poking, right? So that's not how you do it. You actually design the matching network into your circuit. So there are many ways to do tuning, at least some of them here. Lump elements meaning using a L inductor, the winding of the wire, the coil, as inductor and the chip capacitor. Those are typically used at a lower RF frequency, like 1 gigahertz, 2 gigahertz, 100 megahertz, that kind of thing. Most likely we use transmission line, either it's 50 ohms or other impedance transmission lines. Stubs, open stub, short stub. Single stub tuning, we already talked about it. There's something called double stub tunings. We're gonna explore that. We use quarter wave a lot. Quarter wave, again, is easy if you know the impedance you want to match. And then a lot of these combinations. Sometimes you say, oh, so if I have a circuit, you know, I can use AWR. There's a function called optimization. I just, you know, optimize it, my inductors and capacitor, and it'll work. It won't. It doesn't always work. So what do I mean by that? Let's say you go to work, you're a working engineer. So last time people design a amplifier by buying a Mimix here and bias it. And then on this side, here's a shunt capacitor and the inductors. And so that would match. This one has a shunt capacitor and series capacitor here. It will match. So now this is my input matching network and output matching network. Right. So let's say this is what the company's been doing. And now later on, we either buy another Mimic chip, the semiconductor chip, or we just do the same design but at different frequency, a different bandwidth, or whatnot. And then so your boss say, okay, can you redesign this matching network? I said, no problem. I can draw this in AWR. So this is my L, this is my C. I'm just going to hit optimizations, and AWR would automatically find me the solutions. But it doesn't always work. Really depends on what the impedance is. So you can hit the optimization button all days and it will not optimize. And then you're like, well, a lot of engineers would get stuck. He would say, I never done this before. And you go to your boss, and next time the layoff, you'll be the first one to go. Why? How come it works sometimes and doesn't work in other times? You need to understand it. That's why Smith chart is a really useful tool to understand that. And we're going to go over this. Okay. Smith chart, you can still do Smith chart on AWR, by the way. And a lot of people don't use Smith charts these days because the computer is so powerful. So you can bypass that step a lot of times.
So, Professor?
Yes.
So you said one of the requirements for the exam was, that one of the things we had to do for the exam was bring our own Smith chart. is it, do I have to like a physical Smith chart, like a piece of paper with a Smith chart on it, or?
Yes.
Oh, okay.
Yes.
Okay.
I'm thinking of whether I will allow you to use AWL, but later. But yes, I want you to be able to draw that on a Smith chart, physical Smith chart. Okay, so let's go on. So what is a Smith chart? Let's talk about this. This is a Smith chart, by the way. Okay, so let's go over the basic idea of Smith chart. What is the Smith chart? Smith chart is a chart of gamma. So what do I mean? Is gamma is reflection coefficient. So you're really plotting the reflection coefficients here. Remember, we say the gamma, I can write it in polar form. This is the magnitude of reflections, and this is the phase of your return loss, of your reflections, right? So in the polar form, so if I would draw this in polar coordinate, the real part, I'm going to call it U. The imaginary part, I'm going to call it V. So on the x-axis, I have U. On the y-axis, I have V. So I'm really plotting gamma on this chart. On this chart, so if any point here on the chart, the radius here is so any point on the chart. So let's say this point, the radius from the center, that's my rho, right? That's the magnitude of my reflection coefficient, the reflections, and the angle here, that's my theta. Right. So if I know the reflections and in polar coordinate, I can calculate it, also plot it in real and imaginary, in rectangular coordinate, right? So all the polar coordinate and the rectangular coordinates are all here. Okay. So, but what is gamma? Gamma is related to impedance also, right? Because gamma is equal to C. Normalize it, it's C naught plus 1, C bar minus 1, C bar plus 1, right? So so I can also look at plot this as a function of impedance. Okay. Remember, one thing you want to remember is Smith chart always use normalized parameter. The impedance and admittance, everything has to be normalized. Smith charts has to be normalized. Okay. Okay, so let's look at some of the parameter again. So let me rewrite it. It's rho e to the j theta. So what is the maximum value of rho? What is the maximum? The biggest number of rho?
The 1?
1. 1 means 100% reflections, right? You cannot have more than 100% reflections, right? So rho has to be equal or less than 1. So if I draw rho is 1, this is a 1 circle. So that means that this is the origin, the radius is equal to 1. The green circle here, that dictate everything is that the green circle means rho is equal to 1. The radius is equal to 1. So physically, anything, all reflection coefficients has to be less or equal to 1. So that means we only look at this portion of the chart. Anything outside of this circle, those are not realistic, right? Those are not real for me. Not a realistic situation, right? Physically impossible. So I'm only interested in everything inside this 1 circle, reflection 1 circle. Okay. All right. No questions? Let's look at the next page. So let's look at the a little math again. I promise you it won't be a lot. So this is my reflection coefficients in terms of normalized impedance. So I can turn it around and solve for Z, right? It's a function of gamma. We did that, I think, right? From this, I can turn into this, linear algebra. So what is gamma? In terms of real and imaginary rectangular coordinate, I'm going to write gamma as U plus JV. Again, U is the real part, J is the imaginary part. So I get this. Okay. Now, this is a complex number. If I want to rationalize the denominator, and that means I want to make the denominator to be real number, I multiply it by a complex conjugate, right? So that means this is the complex conjugate of this. This is 1 minus U, the real part, minus JV. The complex conjugate is 1 minus U plus JV. I do that to top and bottom, right? And so now my denominator becomes this, and my numerator, when I multiply out and group it, becomes this. That's my Z bar. What is Z bar? Again, the real part is resistance, the imaginary part is reactance. And this is supposed to have a bar. I'm just getting tired to write a bar. So this is supposed to be R bar plus JX bar. I'm just going to skip all the bar, right? Anything I write from this point on are normalized. Okay, so R is really actually R bar, normalized resistance. And so now I can solve for this. The bottom is real already, right? Right? So now this is a complex equation. I'm going to equate the real part with the real part on this side. When I cross multiply this, the real part is R times the denominator. That's equal to the real part of the numerator, right? So that's one equation. So let's look at this equation again. I'm going to multiply out, taking U is my variable. I collect the like terms. So this is my constant term. This is my quadratic terms, my linear terms, right? I can remember all the algebra techniques that you learn in middle school. I can complete the square, or I can divide everything by R plus 1. So I get this, U square, U and constant. And to do a complete square, I square this, right? I subtract this. Let's see, did I do that? Yeah. So this turns out to be a constant already. The constant is here. I'm going to group them. So I have, I complete the square, right? I make this U minus half of this, make this a complete square. And so I have extra terms I need to subtract, which is this one out. And then this is the constant term, right? And then V squared is still here. Remember, complete the square in middle school? If you don't, let me know. I assume you do. So now I will, x squared plus y squared is equal to a constant square. That's my circle equation. Remember circle equations? No, you don't. So x squared plus y squared is equal to r squared, right? R is the radius. That's the circle, right? This is right? Right?
Right.
Okay, if you don't remember,
Yeah.
go back and look at it. I'll take my words for it. So that means now x and my variables are not x and y. My variables are u and v. So this is like, my first variable, second variable. This is a circle equations. The equation of circle with the real, the horizontal axis is my x, the vertical axis is my y, and R is a constant, right? R is a resistance, is a constant for fixed resistance. So let's say let me look at if R is equal to 1. What does that mean? So I have U minus 1/2, right? Square plus V square is equal to R is equal to 1. So this is 1/2, right? So the circle is a circle with a center shift half a unit to the right. So I have this circle here, where the center is half unit, right? So this is my R is equal to 1 circle. I always call this the 1 circle. What does that mean again? This is when R is equal to 1. What does R is equal to 1 means? The normalized resistance is equal to 1. So if we are looking at a 50 ohm system, if everything is normalized to 50 ohms, this circle is a 50 ohm circle. That means any point on this circle, on the circumference of the circle, has a real part resistance equal to 50 ohms. Is that clear? Let me repeat that. For R is equal to 1, this is the so-called 1 circle. Any point here has R is equal to 1, because that's how we draw this circle, right? The circle represents R is equal to 1, and the U and V are the variables.
So what about between R equals 1 and R equals 0? Is that like a fraction?
In between, we will talk about that later. Okay, just hold on.
Okay.
So, of course, if I look at this equations, depends on what R is, right? I mean, this equation is down here. Depends on what R is, a different R will give me a different equations. So in other words, if I plug in different R in here, I will get a different equation, I will get a different circle. So for example, if I plug in R is equal to 0, then I get U squared plus V squared is equal to 1. That's my R is 0 circle. That's my biggest circle. That's the gamma is equal to 1 circle. Right? So this one, any points on this circle, gamma is equal to 1, R is equal to 0. Any point on this 1 circle, R is equal to 1. This is 50 ohms. Anything in between, yes, you can just plug in different R. So you basically get a family of circles like this in a Smith chart. Okay, each circle here represents different R. If I'm looking at this circle, R is equal, the resistance is equal to 1. If I'm looking at this circle, R is equal to 2, for example. R can be equal to 0.5, for example, right? So you have a lot of circles, a family of circle like this. The unique thing is this one always on this side. This edge doesn't move. Only the center move and the radius move. Right? So looking back to my Smith chart, by the way, you have a Smith chart on Canvas. You can download it and print it. You see all this circle here? This is the circle we're talking about. This are the family circle. You see all this, like so many, right? And it's all this circle. You see that?
Yeah.
Those are called constant resistance circle. That means if I just look at following one circle, any points on this line, on this circle, on the circumference of this circle, it has the same constant resistance. The imaginary part will change, but the real part, the resistant part, stay the same if I stay on the same circle. Right? So
Got a question?
Yes.
So if the biggest circle, the one centered at the origin on the UV,
Green circle.
yes, so the max reflection circle,
Yes.
that means that, let's see, that means that the magnitude of gamma is 1. So it also means that the normalized resistance is 0.
No. So, I probably said that wrong. Okay, no. So let's look at this one. So basically, this is my Smith chart circle.
But it says it right there. Normalized R equals 0. So what is
R
that?
is 0. Oh,
So does that mean a purely imaginary load, or?
So is or
yes, imagine, yeah, purely reactance.
Okay.
Let me think about this.
so R equal to 0, isn't that the point? Like the
It's
the
a
point-
circle.
right?
So
And
if you plug R is equal to 0 in this formula, that's a good question. In this formula, you will get U squared plus V squared is equal to 1. Right? You get a
Yes.
circle.
And similarly, if resistance goes to infinity, you're stuck on the very rightmost part of the graph on the U axis. Where
I'm sorry, say
still-
it again. I'm sorry, say it
so
again.
if the resistance, the normalized resistance goes to infinity, you're also stuck on the R equals 0 circle.
Right.
Interesting.
So that means open and short are on the same circle. Good question. I need to think about that too. Okay. So let me move on. Do I have time? No, I don't have time. So let me just summarize what we have done here. So we look at Smith chart. Basically, we only look at that. We say by solving the real part of these equations, we get a family of circles, right? For high impedance, for high resistance, this is R is equal to, say R is equal to 2, R is equal to 3, that the circle is getting smaller and smaller. For smaller impedance, let's say R is 0.5, 0.4, 0.1, the circle is getting bigger and bigger, and eventually R is 0 will be the biggest circles. I get this family of circles. This type of circles I call constant resistance circle, right? So next time we look at the imaginary part of these equations, and we get another family of circles, and putting those circles together, we get the Smith chart. And then from that point on, we have to learn, what does that mean? How do we use it? Why is it useful for us? How do I use it to do impedance matching and to try to get some physical meaning of it? Okay. Any questions?
Professor, I have a question regarding HFSS.
Yes.
So, unless someone else posted, like when I checked the discussion I made, no one else had the same issue as me, so I still can't get HFSS working. Should I talk to, or can you direct me to someone that can help me with that?
Yes. Yes. Do you get an error message when you run it, and what does it say? Can you screen capture that?
Yeah, it was let me pull it up. Or I posted it in the discussion, and I posted.
Oh, okay. So I'll look at it, and let me route that to the ANSYS guy and see if they can tell me what's wrong. If not, if we cannot resolve it that way, then I will ask them to assign a technical person to help us.
Okay, thank you.
Okay.
So I had a question about FHSS. So,
Yes.
so when I'm doing the evanescent waveguide filter, so when you do the FHS, you do the E fields on it, and that way you can see